Welcome to this explainer. If you've ever felt totally boxed in by arrays that just won't grow, or honestly just frustrated by memory that completely disappears the second a function ends, you are absolutely in the right place. Today, we're going to journey from the restrictive, padded room safety of automatic memory allocation straight into the raw, unbridled power of dynamic control in C. We are going to completely demystify exactly how memory works under the hood.
We begin our journey right where almost every beginner C programmer starts out.
This is the realm of automatic memory, also known as the stack. It's safe, it's predictable, and honestly, it asks very little of you. Think about how memory is provisioned and released here. You declare an integer, maybe a character, a pointer, an array, and boom, C just handles it behind the scenes. You don't have to explicitly beg for the space. And even better, when the compiler hits that closing bracket, all of that memory is automatically released without you having to type a single command. It feels like magic. But as you'll see, that convenience comes at the cost of absolute control.
However, this automatic system actually creates a bit of a paradox, specifically when we look at read-only pointers versus mutable arrays. When C handles things for you, it silently categorizes memory in ways that aren't super obvious at first glance. And stepping out of those invisible bounds, well, it leads to instant punishment.
Let's look at the string literal paradox. Imagine you have a pointer directly referencing a string literal, like the word university. The system essentially puts a padlock on that memory. It is strictly read-only. If you try to jump in and change that capital U to a lowercase s directly, you get hit with a catastrophic segmentation fault, just an instant crash. But by simply using standard array syntax instead, C does something really clever. It creates a mutable, editable copy of that exact string right on your local stack. Now, making that identical change to the U works perfectly, printing out exactly what you wanted.
Your programs have to handle the unpredictable real world, and the stack just can't adapt. This brings us to a huge question. What if you don't know a file's size? When you compile C code, the compiler strictly demands to know exactly how big your automatic arrays are going to be. But practically speaking, how could you possibly know the size of a text file a user is going to upload before they actually upload it?
So you end up playing a guessing game. And guessing array sizes leads to two terrible outcomes: not having enough space or wasting massive amounts of memory. If you declare an array of 1,024 words, but the file turns out to have 2,000, your program overflows and fails. If you panic and declare an array of 1,000,000 words just to be totally safe, but the file only has 10, you are wasting an enormous grid of memory for absolutely no reason. Simply put, if your size depends on file content, user input, or if the data has to survive after a function ends, you have to leave the stack behind. You're no longer asking the compiler to guess. You are taking the wheel yourself. This weapon is called malloc, short for memory allocation. It's a command that allows you, the programmer, to manually claim space directly from the heap at runtime. Now, the heap is just this massive pool of unallocated memory, sitting outside the restrictive bounds of the stack. To use it, you just have to remember to include the standard library header, stdlib.h. The syntax for seizing control here is surprisingly straightforward. You just request a specific number of bytes, and the heap grants you a pointer to that exact block of memory. So you ask malloc for 3 characters worth of space. The heap finds that space, carves it out, and hands the address back to your pointer. From there, you can populate it with whatever you need. You are manually mapping your data directly into the computer's memory architecture. But here is a crucial rule. Never, ever request raw byte numbers. The gold standard is using the sizeof operator. This ensures your code calculates exactly what it needs dynamically, so it works flawlessly on literally any system. If you just ask for 12 bytes because you assume an integer is 4 bytes, your program will fail catastrophically on a system where integers are sized differently. Using sizeof is much better, but the absolute top-tier gold standard is using sizeof on the pointer variable itself. It's totally self-documenting. If you decide to change the variable type later from an int to a double, the compiler automatically adapts to the exact byte requirement. It's completely foolproof. Here is the peril. Because with this great power comes an incredibly high level of responsibility and severe risk. The heap does not hold your hand. Imagine a developer's worst nightmare, a memory leak. This is where the pointer is destroyed, but the memory remains locked away, completely unreachable and unrecoverable. Imagine you have a pointer on the stack, happily pointing to a block of memory you claimed on the heap. Great. But when that function returns, the stack clears automatically, meaning your pointer just vanishes. But that heap memory, it just sits there.
The address is destroyed, the bridge is burned. You can never reach that memory again to use it, and you can't free it. It is entirely lost to your program. And if your massive memory request fails and you try to use it anyway, the consequences are completely fatal. The heap is huge, sure, but it isn't infinite. If the operating system refuses your request for memory, malloc won't crush your program right then and there. Instead, it subtly hands you a null pointer. To survive, you must intercept the danger. You need a vital safety check to ensure malloc didn't hand you a dangerous null pointer. If you skip this check and try to assign data to a null pointer, your program crashes instantly. It's a fatal error. You must always check. The absolute second you call malloc, you need to write an if statement checking if the pointer is null. If it is, you exit gracefully before ever touching the memory. So how do we rescue ourselves? How do we manage the infinite thread of memory that never goes away on its own? We need discipline, and we need the right tools. The mandatory cure here is the free command. You absolutely must use it to return the borrowed memory back to the system to maintain stability. Think about a while loop that endlessly calls malloc. Since dynamic memory never cleans itself up, the pressure builds and builds until the operating system violently kills your program. The blueprint to fix this is simple. You get the memory, you use the memory, and before that pointer is ever lost, you give it back by calling free. That mandatory cleanup is what keeps your entire system stable and leak-free. And to be absolutely certain you haven't caused a leak, you use Valgrind. Think of it as our personal memory detective that will flag if you've lost bytes or praise you if all heap blocks were freed. If you run your program through Valgrind and the terminal says definitely lost X bytes, it means you forgot to free something. That broken link we talked about earlier just happened. If it says invalid read/write, you're touching memory you shouldn't be. But when you see that beautiful text saying all heap blocks were freed, you know your code is perfect. No leaks are possible. Let's lock in everything we've covered into a framework of mastery. Because understanding the theory is only half the battle. It really comes down to this ultimate trade-off between automatic safety and developer-controlled power. On the stack, C handles allocation when a function is called and frees it when it ends. You have to know the size at compile time, it cannot resize, but there's virtually no risk. But on the heap, you allocate with malloc. You free with free. You control it. The size is decided at runtime, it can be resized, but the primary risk is entirely on your shoulders. Memory leaks if you forget to clean up. So your complete dynamic lifecycle boils down to exactly 4 steps. Step 1, dynamic request using sizeof. Step 2, the safety check, instantly catching the null pointer. Step 3, safe usage of the heap memory. And step 4, strict cleanup, calling free right before the program returns. That right there is the perfect anatomy of a dynamic C program. Honestly, burn these rules into your brain. This is your definitive checklist to manage dynamic memory successfully. Avoid the traps, forgetting standard lib, using raw numbers instead of sizeof, overwriting pointers before you free them, or the dreaded double free, trying to free the exact same pointer twice. Instead, live by the absolute laws. Every single malloc needs a one-to-one free. Always check for null. Never, ever touch memory after you've freed it. And always verify your final work with Valgrind. Dynamic memory gives you absolute control over the machine. The training wheels are off. You now have the exact blueprint to command the heap, to allocate dynamically, and to write truly powerful, scalable programs. The machine is yours to control, but that control demands absolute discipline. So I'll leave you with this final thought as you write your next lines of C code. Are you disciplined enough to clean up after yourself? Thanks for joining me on this explainer, and happy coding.